Thanks, Danny. And thanks, Rahaf. Very interesting section. Let me talk about an example of a continuous learning system that we worked on in my research group over the past decade. We call this our never-ending language learner. And so what I want to do in this presentation is briefly describe the system, but then really focus on what are the lessons that we learned from trying to build this system that might apply to continuous learning systems in general. So our never-ending language learner, we call it NELL. Here is the task that we gave it. The goal is for the system to run continuously, continuous learner. By the way, I'll just remark that despite the huge uptick in the number of research papers and projects on continuous learning, there are very few systems that continuously learn. So much of that research is kind of on different components of the problem, but there are very few integrated systems that run 24/7 forever. So in NELL, the goal was for each day for the system to do two things. One was to extract more facts from the web, the unstructured text on the web. And the second was to learn to do that better each day. That is, to learn to read the unstructured information on the web better each day. To do this, the inputs to the system were an initial ontology that defined categories and relations of interest in the ontology. For example, people, beverages, emotions, buildings could be categories of interest. Relations might be person works at company, or this type of clothing is worn with this type of clothing, and so forth. For each of these categories and relations in the ontology, we provided NELL labeled examples, about a dozen labeled examples of each. So if we said person is a category, we'd give a dozen noun phrases, Daniel Silver, for example, as an example of a person. But primarily, NELL had to learn from the unlabeled data on the web. And I think that's really indicative of the kind of continuous learning that almost any agent will be confronted with. It'll be maybe a little bit of supervised data, but a lot of unsupervised or weakly supervised. We also allowed occasional interaction with human trainers, though in the end that was a pretty small component of the system. Okay, so there's the continual learning agent problem. We did develop such a system. It ran for 8 years. We ended the project in 2018, but it did run continuously for 8 years. It built up a knowledge base with over 100 million belief triples, like Bill Gates founded Microsoft, with some confidence weighting on each. And it did learn in various ways. So let me first show, when I say that it built up a knowledge base over time of 100 million beliefs, here's a sample of that knowledge base. For example, each red arrow here represents a triple, a belief triple. So for example, the Maple Leafs play hockey. That would be a belief. The Maple Leafs won the Stanley Cup, which was also won by the Red Wings, whose hometown is Detroit, which contains a company called GM, which competes with Toyota, which is in the economic sector automobile. So you get the idea. Fairly diverse knowledge base or knowledge graph that the system was able to build up over these 8 years. It did, in fact, improve over time in a couple different ways. One is you can track over time the size of its knowledge base, and that grew, of course. But maybe more interestingly, its precision for reading, its reading skill, improved over time. That is, by year 2, it was actually more accurate than it was when we started it. in terms of being able to look at unlabeled text on the web and extract new beliefs. So its accuracy increased over time. So what are the lessons we learned from this? One of them, I would say the primary lesson, if you remember one thing from this talk, here's the one I want you to learn. It'll take me 2 slides to present it. But the lesson is that if you're trying to learn various functions with semi-supervised training, which is exactly what NELL had to do. For example, we give it a dozen examples of people, but then we give it all the unlabeled data on the web, and we want it to learn to become increasingly accurate at reading text and spotting noun phrases that refer to new people. If you set that problem up in the most obvious way, that you're trying to learn some function from noun phrases to person, and you want to learn that with a little bit of labeled and a lot of unlabeled data, that turns out to be way too hard to succeed in. And it turns out, this is the lesson, it's much easier if instead you force the system to do massively coupled semi-supervised learning of many different functions. And I'll expand on that here. So for example, suppose you're trying to learn a function that goes from a noun phrase, NP noun phrase, that you find on the web to label yes or no, is this a person? And we might represent that noun phrase by an input vector indicating how often that noun phrase occurs in different contexts. That we might see Daniel Silver as a friend. We might see rang the Daniel Silver, but if Daniel Silver is a person, then rang the Daniel Silver is not going to be a very frequent context that we see him in, and so forth. So in NELL, we had several million of the most common contexts that noun phrases occur in, and represent each noun phrase by simply how frequently it occurs in each of those millions of contexts. And then you can imagine you could train a neural network or a logistic regression even on that kind of vector representation of a noun phrase to classify whether it's a person. And if you do that in the supervised training way, what you want to do is you want to learn the parameters of your function to minimize the sum over all the labeled examples of how often the prediction of function differs from the true label y. Okay, so that would be standard supervised learning. Now, here's how you make coupled supervised learning work in your favor. Suppose in addition, you decide to learn a second function. So in general in this talk, black arrows are functions we're trying to learn. So suppose instead of representing the noun phrase by the context in which it occurs, we just represent it by, say, the sequence of characters in the noun phrase. Is that sequence of characters capitalized? Does it end with SKI? Does it contain different substrings and so forth? Now, in this case, if you think about the objective that we want to train, well, now we want to minimize both theta 1 and theta. We want to train jointly theta 1 and theta 2 to, of course, continue to minimize the errors over the labeled data. But most importantly, now we can use the unlabeled data, because even though if you give me a new noun phrase and it's unlabeled, you don't tell me whether this is referring to a person or not. I do know that if both of these functions are correct, F1 and F2, then they must agree. If they disagree, at least one of them is wrong. And so, I guess one of them is wrong. And so we can add a new term to the objective that we're optimizing that allows us to jointly choose the parameters theta 1 and theta 2 to minimize disagreement, to maximize the consistency of the predictions that these functions make on the unlabeled data. And that's the key idea, because if we couple the training of multiple functions, then we can provably, it turns out, use unlabeled data to improve the accuracy of the trained functions. And in fact, we have some theoretical results on this that show that if these two functions are path learnable from noisy labeled data, and if the inputs that you're using to code the input are conditionally independent given that label, then we can actually path learn those functions from unlabeled data, as long as we start with estimates that are better than chance. So a little bit of labeled data will give us functions better than chance. And then we can finish off the job with unlabeled data. So in NELL, we use this in many ways. So for example, I'm going to skip over that. I'll say, in addition to coupling the training of two different functions that predict the same label from different views of the input noun phrase, we also trained multiple functions to predict different labels. So given a noun phrase, we might want to know whether it refers to a person, but also whether it refers to a sports team or a sport or a coach or an athlete. And so in this case, we had multitask learning with different Boolean valued functions here. But importantly, we could use background knowledge about, for example, which categories are subsets of which. Athletes are a subset of people. And so if NELL learns to predict for a certain noun phrase that it represents an athlete, then it must also predict that it's a person. To predict that it's an athlete and then have a different function predict it's not a person would be inconsistent. So here's another kind of consistency constraint. Similarly, there are a lot of mutual exclusion consistency constraints. If something is a sport, then it's not an athlete. Okay, so yes.
Tom, just a couple minutes.
Okay,
Yep.
Got it. So the idea is by bringing in both of these types of coupling constraints simultaneously, using multiple views and predicting multiple labels with consistency constraints among the labels, we can do much better. A third type of coupling constraints in NELL had to do with learning relations, two argument relations, but these are typed relations. And so, for example, the relation play sport requires that the first argument be an athlete and the second argument be a sport. And so now the functions that we're predicting category membership of noun phrases have to be consistent with the functions that are predicting which relations hold between pairs. And so this leads to a nest of interconnected, in fact, thousands of coupled functions in NELL that are interconnected by these different constraints. Now, if you go back to Rahav's talk, which preceded this one, it would be interesting to think about that issue of catastrophic forgetting in these terms. For example, what if we took into account that trucks were mutually exclusive from bicycles or something like that? If we had that kind of background knowledge, how would that change our ability to address catastrophic forgetting? So I want to end there, and because I want to have some time for discussion. But I think if you get, if you're interested in other lessons from the NELL project, please take a look at our CACN paper from 2018. But if you get one lesson out of this talk, it's this. My belief is that if we want to make progress on continuous learning, then number one, we should be looking at agents that learn and agents that contain multiple functions. They might be represented by neural nets or other ways, but we should be looking at architectures of agents that learn multiple functions. and finding ways to architect those agents so that instead of requiring label data and training on the objective of minimizing errors over label data, we find ways to instead use an objective that is effectively forcing the agent to become increasingly consistent in the multiple coupling, taking into account the multiple coupling constraints that the agent has, and in fact can learn over time. Okay, thank you. I'm going to stop there so we can have some discussion.